According to the National Electrical Code, specifically Article 300.22 of the 2020 edition, conductors of the same circuit, including grounding conductors, must be grouped together and enclosed within a single raceway, cable, armor, or other approved enclosure. This requirement means that all conductors belonging to a circuit, including the phase conductors, the neutral conductor, and the equipment grounding conductor, must be contained within the same conduit or raceway system. The reason for this requirement is to ensure that all conductors are adequately protected from external damage and potential interference. It also ensures that the magnetic fields generated by the phase conductors are properly contained. Separating the conductors can lead to increased magnetic fields and potential interference between circuits. If the neutral conductor is run separately from the other conductors, as in a separate chase nipple, it violates the NEC requirement for grouping conductors of the same circuit together. This type of installation is not acceptable under the NEC guidelines. All conductors of the same circuit, including the neutral conductor, must be enclosed within the same raceway or conduit system. It is imperative to request that the contractor correct the installation by grouping all conductors of each circuit together in a single conduit or raceway. The NEC mandates this grouping for several important reasons. Firstly, it minimizes the impedance of the circuit. When conductors are separated, the inductance of the circuit increases, which can lead to voltage drops and inefficient operation. Keeping all conductors together allows for the magnetic fields created by the alternating current in the phase conductors to effectively cancel out the magnetic field created by the current in the neutral conductor. This cancellation reduces the overall impedance of the circuit. Secondly, the NEC requirement helps prevent overheating of the conductors and surrounding materials. Separating the conductors can cause eddy currents to circulate in nearby metallic objects such as the metal enclosures of the electrical panels. These eddy currents generate heat, which can damage the conductor's insulation and other components. By keeping all conductors together in a single raceway, the magnetic fields are contained and the risk of eddy currents is minimized. Thirdly, grouping conductors together improves the overall safety of the electrical system. If a fault occurs in one of the phase conductors, the fault current will flow back to the source through the neutral and grounding conductors. When these conductors are grouped together, the impedance of the fault current path is minimized, allowing the protective devices, such as circuit breakers or fuses, to quickly detect the fault and interrupt the circuit. This fast response time reduces the risk of electrical shock, fire, and equipment damage. Fourthly, the NEC requirement for grouping conductors helps to reduce electromagnetic interference, also known as EMI. Separating the conductors can cause the circuit to act as an antenna, radiating electromagnetic energy that can interfere with nearby electronic equipment. By keeping all conductors together in a single raceway, the electromagnetic fields are contained, and the risk of EMI is minimized. This is particularly important in environments where sensitive electronic equipment is used, such as hospitals, laboratories, and data centers. Fifthly, proper grouping of conductors ensures compliance with industry standards and best practices. The NEC is a widely recognized and respected standard for electrical installations. Following the NEC requirements demonstrates a commitment to safety and quality. It can also help to avoid costly rework and potential liability issues. When inspecting an electrical installation, there are several key things to look for to ensure that conductors are properly grouped. Firstly, verify that all conductors of the same circuit, including the phase conductors, the neutral conductor, and the equipment grounding conductor, are contained within the same raceway, cable, armor, or other approved enclosure. Secondly, check that the raceway or enclosure is properly sized to accommodate all of the conductors. The NEC provides tables and guidelines for determining the appropriate size of raceways and enclosures based on the number and size of the conductors. Thirdly, ensure that the conductors are properly identified and labeled. The NEC requires that all conductors be clearly identified as to their function, such as phase conductor, neutral conductor, or equipment grounding conductor. This helps to ensure that the conductors are properly connected and that the electrical system is properly maintained. Fourthly, verify that the raceway or enclosure is properly supported and secured. The NEC requires that raceways and enclosures be supported and secured in a manner that prevents them from being damaged or dislodged. This helps to ensure the long-term reliability and safety of the electrical system. Fifthly, inspect the conductors for any signs of damage, such as cuts, abrasions, or discoloration. Damaged conductors can pose a safety hazard and should be replaced immediately. When correcting an improper installation where conductors have been separated, there are several steps that should be taken. Firstly, de-energize the circuit. This is essential to prevent electrical shock. Secondly, remove the existing conductors from the separate raceways or enclosures. Thirdly, install a new raceway or enclosure that is large enough to accommodate all of the conductors. Fourthly, pull all of the conductors into the new raceway or enclosure. Fifthly, properly terminate the conductors at the electrical panels or other equipment. Sixthly, test the circuit to ensure that it is working properly. It is important to note that electrical work can be dangerous and should only be performed by qualified electricians. If you are not comfortable working with electricity, it is best to hire a professional. In addition to the NEC requirements, there may be local codes and regulations that apply to electrical installations. It is important to check with the local authorities to ensure that all applicable codes and regulations are followed. In summary, the NEC requires that all conductors of the same circuit, including the phase conductors, the neutral conductor, and the equipment grounding conductor, be grouped together and enclosed within a single raceway, cable, armor, or other approved enclosure. This requirement is essential for ensuring the safety, reliability, and efficiency of the electrical system. Separating the conductors can lead to increased impedance, overheating, electromagnetic interference, and potential safety hazards. If you observe an installation where conductors have been separated, it is important to take corrective action to bring the installation into compliance with the NEC and other applicable codes and regulations. Furthermore, the concept of maintaining a low impedance path for fault currents is crucial for effective ground fault protection. When the neutral and grounding conductors are separated, the impedance of the ground fault path increases significantly. This increased impedance can limit the magnitude of the fault current, which may prevent the overcurrent protective device, such as a circuit breaker, from tripping quickly enough to clear the fault. The result can be a dangerous buildup of voltage on the equipment grounding system, posing a shock hazard to personnel. To ensure a low impedance ground fault path, the equipment grounding conductor must be run in the same raceway or cable as the circuit conductors. This minimizes the inductive reactance of the fault current path, allowing for a higher fault current magnitude and faster tripping of the overcurrent protective device. Additionally, the equipment grounding conductor should be properly sized according to the requirements of the NEC based on the size of the circuit conductors. The NEC provides tables that specify the minimum size of the equipment grounding conductor for various circuit conductor sizes. Another important consideration is the type of raceway used to enclose the conductors. Metallic raceways, such as steel conduit, provide an effective ground fault path and can help to reduce electromagnetic interference. Non-metallic raceways, such as PVC conduit, do not provide a ground fault path and require the use of a separate equipment grounding conductor. When using non-metallic raceways, it is essential to ensure that the equipment grounding conductor is properly sized and installed to provide a low impedance ground fault path. In addition to the requirements for grouping conductors and providing a low impedance ground fault path, the NEC also addresses the issue of voltage drop. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to the impedance of the conductor. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of electrical systems, and even damage equipment. To minimize voltage drop, the NEC recommends that conductors be sized so that the voltage drop does not exceed 3% for power, heating, and lighting circuits, or 5% for feeders. The voltage drop can be calculated using the following formula: voltage drop equals current times impedance. The impedance of the conductor depends on the length, size, and material of the conductor. To minimize voltage drop, it is important to use conductors that are large enough for the load they are serving and to keep the length of the conductors as short as possible. In addition to sizing the conductors properly, it is also important to ensure that the connections are tight and corrosion-free. Loose or corroded connections can increase the resistance of the circuit, which can lead to increased voltage drop and overheating. To prevent loose or corroded connections, it is important to use properly rated connectors and to tighten them to the manufacturer's specifications. It is also important to inspect the connections regularly for signs of corrosion and to clean or replace them as needed. The NEC also contains requirements for the installation of electrical equipment in hazardous locations. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dusts. In hazardous locations, it is essential to use electrical equipment that is specifically designed and rated for use in those environments. The NEC classifies hazardous locations into different classes and divisions based on the type and concentration of the hazardous materials that are present. Each class and division has specific requirements for the type of electrical equipment that can be used in that location. For example, in Class 1, Division 1 locations, which are areas where flammable gases or vapors are present continuously or intermittently, it is necessary to use explosion-proof electrical equipment. Explosion-proof equipment is designed to contain any explosion that may occur inside the equipment, preventing it from igniting the surrounding atmosphere. In Class 2, Division 1 locations, which are areas where combustible dusts are present continuously or intermittently, it is necessary to use dust ignition-proof electrical equipment. Dust ignition-proof equipment is designed to prevent dust from entering the equipment and igniting. The NEC also contains requirements for the installation of electrical equipment in healthcare facilities. Healthcare facilities have unique electrical requirements due to the presence of sensitive medical equipment and the need to provide a safe environment for patients. The NEC requires that healthcare facilities have a reliable source of power and that the electrical systems be designed to minimize the risk of electrical shock. In healthcare facilities, it is essential to use isolated power systems in patient care areas. Isolated power systems are designed to limit the amount of current that can flow through a person if they come into contact with a live conductor. The NEC also requires that healthcare facilities have a comprehensive grounding system to minimize the risk of electrical shock. In addition to the requirements for grounding and isolated power systems, the NEC also contains requirements for the installation of emergency power systems in healthcare facilities. Emergency power systems are designed to provide power to essential equipment such as life support systems and lighting in the event of a power outage. The NEC requires that emergency power systems be tested regularly to ensure that they are functioning properly. Finally, the NEC emphasizes the importance of proper overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds the rated capacity of the conductors. Short circuits occur when there is a direct connection between two conductors that have different voltages. Overcurrent protection devices are designed to interrupt the flow of current in a circuit when an overload or short circuit occurs. This prevents the conductors from overheating and potentially causing a fire. The NEC requires that overcurrent protection devices be properly sized and installed to protect the electrical circuits. The size of the overcurrent protection device should be based on the ampacity of the conductors that it is protecting. The ampacity of a conductor is the maximum amount of current that the conductor can carry without overheating. The NEC provides tables that specify the ampacity of different types of conductors based on their size, material, and insulation. In summary, adhering to the NEC guidelines, especially regarding conductor grouping, grounding, voltage drop, hazardous locations, healthcare facilities, and overcurrent protection, is paramount for ensuring electrical safety, reliability, and efficiency. These standards are designed to protect people and property from the hazards associated with electricity.